Okay, in this video we're going to talk about expectation and the expected value function. We'll start off with a quick introduction. Imagine you roll a die. This is a six-sided die, right? That same die that you use in bobbing. And you roll it 120 times, right? So you can imagine you have 120 results. You know, you see a bunch of ones and sometimes you see twos and sixes and fives and threes, right? And we're saying, okay, if I counted up all the times that it was a six, how many sixes would I expect if I rolled it 120 times? Well, hopefully this is kind of obvious to you. There's the probability of rolling a six on any given roll is 1 out of 6. And since there's 120 rolls, we'd expect 1/6 of those rolls to be 6. And so to figure this out, we would just multiply 1/6 times 120. Right? So it's important to understand what these are. Right? The 1/6 was the probability, and the 120 was the number of rolls. Right? And so if there's n trials in an experiment, and the event has a probability of p, then the expected value is just n times p. So another example of this is a footballer kicks a goal. He has 3/4 chance of being successful, right? So you can imagine maybe you're doing a penalty shot on any given kick. The probability that you make a goal is 3/4, or 0.75. So let's imagine this guy got 12 chances. How many goals would you expect him to kick? Well, in this case, n is 12 because you're getting 12 chances. Your probability is 3/4, and so you'd expect 3/4 times 12 of them to go in, which is 9. So you'd expect him to get 9 goals, right? And hopefully, that's not too mind-blowing, but that's like the underlying concept behind what we're actually going to talk about here. We can talk about the expected value, or is also as a mean outcome for a trial of an experiment. So here's another example. Suppose we have 10 counters. We have 1 with the number of 1, 4 show the number 2, and 3 show the number 3, and the other 2 show 4. Right? And we're going to randomly put these in a hat and pull them out. And we're going to do this 10 times, obviously with replacement. We could summarize these results in this table, right? So the outcomes, the random variable here is what number do we pull out? Well, we could pull out a 1, a 2, a 3, or a 4, right? So those are our individual possibilities. Those are our xi, right? The things that could happen. And then the pi are the probabilities of those things happening, right? So the probability of pulling out a 1 is 1/10 because there's only only 1 out of 10 of these counters are 1s. Probability of a 2 is 4/10, 3/10, 2/10, right? Just to review what we talked about last time, we could create a probability distribution via a spike graph. And I'm going to put 10 here, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are x and these are our probabilities. You'd have a 1, 4, 3, 2, right? This would be a spike graph for that situation. We know it's a probability distribution because if you add them all up, you get 1, right? And no single probability is greater than 1. And then what we talk about is, okay, if I do this 10 times, right? So far we haven't considered the fact that we did it 10 times. If I do this 10 times, how many times would I expect to get a 1? Well, again, we're just doing p times n. So probability of 1 is 1/10 times 10 times is 1. Probability of getting 2 is 4 out of 10 times 10 is 4, right? Probability of getting 3 times 10, and again, we're multiplying by 10 because we're doing 10 trials. We could just as easily do 20 trials or 15 trials, in which case you just multiply this number by however many times you do it. And that's where these numbers come in. And notice we're going to call these things Fi, which is the frequency of each event, right? So the frequency, if I do it 10 times of this is 1, right? So each of these I correspond with I here as well, right? The I being 1, 2, and so on. Or maybe even you start at 0, 1, whatever, right? So what we're trying to look for is what is the expected outcome, right? Like if I did this, what would I expect to happen? And so if I don't know the expected number to come up, basically what we're talking about is what is the mean number, like what is the average number the typical number, right? Mean is typical. What's the typical number that's going to come up? And so remember, to find the mean of anything, we usually typically use x bar. You basically add them all together. You add all the numbers, and you divide by the number of numbers, right? So that's basically what we're going to do, is we're going to add, that's this symbol, the frequencies times the number itself, because we're trying to fit. So basically what's happening is we expect 1 1 to happen, right? So that's what this is representing. We expect 2 4s to happen, right? So another way of writing this is, if I wanted to, I could just write 4 plus 4, right? And then we expect 3 3s to happen. If I wanted to, I could just write this as this, if it makes more sense to you. And then I expect 2 4s to come up, right? I'm sorry, this one over here was wrong. This should have been 4 2s. Right, I expect 2 to come up 4 times. And so the multiplication is just an easier way to do that. It's basically the frequency times the number. If I add all these together and then divide by the number of numbers, the number of numbers is just, how many, 1, 4, 3, 2, how many times you expect this to happen, right? That's what this is saying, is just adding up all the numbers and dividing by the number of numbers. That would simplify into this case, right? Because the bottom piece equals 10, so you could basically just think of this whole thing as, one. You could just think of this whole thing, instead of dividing by 10, you could think of the whole thing as being multiplied by 1/10, right? And then distributing that 1/10 in there, which will then give you this. And so then you notice, okay, well, that mean value, the mu is the same as the sum of the xi, right, the number, times the probability, right? So it's the same idea. So we can now then simplify things. We don't actually need to know the frequency. All we need to know is the xi and the pi, and the corresponding pi, right? So then we get into the general case, which is saying just that, right? The number and the probability associated with that number. If we did n trials, we go through the same thought process, just with variables, and we end up with the population mean, mu, is the same as just the sum of xi times pi, right? And so that's the expected value. And again, part of the reason we're doing this is so you can see how we do these things, right? And so now hopefully you understand that the mean is just given by this expected value. Also, you understand better what this means. You also understand better what this means, right? The population mean is equal to the value of the thing times the probability of that thing, right? This here represents the pi, right? That's what we're doing right now, is they're just giving a different notation for this pi. They're giving this notation right here, all right? So this is best done with an example, right? So find the mean of the magazine store data in example 2. Explain what it means. So the mean, again, is going to be the same as the expected value, and it's given by the sum from I equals 1 to, in this case, 5 of our xi times our pi, right? So we could actually start writing this out. The first one would be 1 times 0.23. If I plug in 2, I get 2 times 0.38. If I plug in 3, I get 3 times 0.21. If I plug in 4, I get 4 times 0.13. If I plug in 5, I get, and we did this problem on a preview, we did this magazine example on the last video. And if you did all this and you add it all up, you get 2.39. And what that means is, on average, you would expect any given customer, if you have a random customer coming in, you would expect that random customer to purchase about 2.39 magazines, right? So that's just the average customer purchased 2.39 magazines, right? The expected value is the same as the average, right? That's what's important to understand. The expected value is the same as the mean of the population, all right? So next we're going to talk about games, right? So if you ever played poker or any casino game, you want to know whether the game is fair or not. You want to know, what are your chances, what's your expected outcome, like how much money are you expected to actually get back. And this actually help you if you go to a casino, understand why casinos have such nice facilities, because the expected value for you is very low, it's negative. The expected value for them is positive. And we talk about expected gain, like how much money would you expect to gain if you played this enough, such as payout. So if a game is fair, that means you're equally likely to lose as you are to win, and the expected value or the expected gain is 0, right? So let's consider this game here. We're spinning a square spinner, so it looks like this. You have 1, 2, 3, and 4 on there. And you want to see what is the expected return for one spin, right? So if I just spin this thing once, how much money would I expect to earn, right? So let's go through this first. These are our xi, our random variable, our x, right? So we can write this probability of x. Our x here, our random variable, is the number on the spinner. And this would be x1, this would be x2, this would be x3, this would be x4. What's missing here is our pi, right? What's the probability it lands on 1? Well, 1/4, right? Because there's 4 equally sized things, assuming that it's, not weighted or something. This is 1/4, this is 1/4, this is 1/4, right? So our pi is actually the same for every single one. What's different is our winnings, right? If I land on different numbers, I get more money. So the expected return is basically going to be the mean return, like on average, how much would I earn? So again, that's just going to be the mean. So the expected value of x, the expected value of this is going to equal the sum of xi times pi from, in this case, 1 to 4, right? So in this case, that's going to be 1 times 1 plus 2 times 2 plus 3 times 5 plus 4 times 4 times 8. This is one way to do it, and then I would divide all this by okay, never mind, I'm thinking about this wrong. So that would be the expected value of like the number you get. What we're actually interested in is the expected value of the like the money that I get. So in this case, we're going to define py, where y is this is a new random variable. In this case, y is our winnings, right? How much we could win. And so in this case, this is our y1, y2, y3, y4, right? This is y1, y2, y3, y4. And we're interested in e of y, not e of x, right? So we're interested in how much money we could win. So I'm going to change this to y times the probability. And so the probability is the same, 1/4 for each one, because it's based on the numbers, right? And so in this case, we would get $1 times 1/4, right? You have a fourth of a chance of getting $1. 2 times 1/4, you have a fourth of a chance of getting $2. 5 times 1/4 plus 8 times 1/4. And if you do all that math, you end up with 4. So on average, you're going to expect your expected return on any spin is $4, right? You expect any random, if you basically, law of large numbers, if you did this enough, you would find out that your average return is $4. You're expected to get about $4 on each turn, right? The next one is, okay, what is the expected gain of the player if it costs $5 to play each game, right? So think about it this way. Expected gain, let's just say expected gain, let's do G, is equal to expected earnings, which is that E of Y, minus expected expenses, which would be how much you have to pay each time. So in this case, the expected gain is you expect to gain $4 each turn, right? Because that's what we figured out here. But then you have to pay $5 each time, right? Yeah, this is the E expected expense is $5. So our expected gain in this case is -$1. So we actually expect to lose $1 every single time we play this game. And so would you recommend playing this game? No, probably not, unless you plan on losing $1 every time that you play. And that's how casinos work as well, right? And a lot of casinos, like the slot machines, you guys are too young to know this, but the slot machines have an expected gain of about 0.86, so expected return of 0.86, meaning every time you play it, you get about 0.86 of your money back, which eventually, that decreases pretty fast if you keep playing it. Okay, so after this, you should try exercise 25C and reach out with questions about any one that you're unsure on how to do, and I'll try to make a video to assist you.